Welcome to EDU World Space.
In the figure at the right, there are infinitely many circles approaching the vertices of the equilateral triangle. And we see each circle is touching other circles and also the sides of the triangle. We're given that the triangle has side length 1, and now we'd like to find all the areas inside the circles. So let's observe that since the side length is 1, this tells us that the median length, so I'll draw that out. I'll draw the median if you forgot what this was. So let's go ahead and draw the median in blue in the picture that we already have. So for this equilateral triangle, we just go to one of the vertices and we just draw the straight line down perpendicular to the opposite side. Again, this triangle that I drew is not perfect at all. It should be symmetric. Equilateral triangle. So it's not the best drawing here, but that's the median, that blue line. So that length, well, if we have side length 1, then this side over here is just 1/2. So we could use Pythagorean theorem to find this opposite side length, √3/2. That'll be the median length. So since this is true, the radius of the circle so let's just call it the first circle. So that's this guy right here, A1. Circle 1, area 1, is given by r equals x/3. And let me explain why. So this is coming from geometry, that the center of the circle is the centroid. So this is a geometry fact of the triangle. So of course by the triangle they mean the as in the picture we have, the triangle circumscribes the large circle. So the radius is median over 3. So this tells us that A equals pi and then x/3 squared, radius over 3, because r was x/3, excuse me. That's why this is my r, median over 3, and then we square that. So let's go on to the next page. So the total sum, before we go to the total sum, notice that the radii of the next 3 identical circles will just be x/9. So the radius of each progressing circle is just 1/3 of the previous. So therefore, we're basically done here. We just have one computation to do. So the sum of the areas is, let's write the sum this way. Let's call it A, and then I will separate A1 from the others because the other ones came in triples and came in 3s. So A1's the area of the large circle. We denoted that on page 1. And then here, this will be my radius of the smaller circles. So pi x pi r squared for my area. So I'm writing the 3 here because those come in 3s, the smaller circles. And then we start dividing by We've already taken out the case where we divided by 3. So this is coming from A1. And then each time we progress, we increase n by 1. So we should be adding n there. So that's the radius for the nth progression. So if you want this guy right here, this would be an plus 1. Now let's go ahead and simplify this. So I'll need more room here. So let me go to the next page. So that's a1. So that's pi. And then we have root 3. Write this out. Getting sloppy here. Root 3 over 2, but then we're also dividing by 3. So that's 4 times 3 squared down there, so that's pi over 12. And then for the other sum, we can rewrite this by pulling out some terms. So this is geometric. And not only that, we could go ahead and simplify some terms over here. So that's a 3, that's a 3, that'll cancel with that down there. So we just get pi over 4 in the front. And then using the formula for geometric series, the first term over 1 minus, what are we multiplying by each time? 1 over 9. That's the r. So now I'm going to come back down here, pi over 4. And then we have 1 over 9 divided by 8 over 9. So that's 1 over 8. So pi over 32. So adding this back to A1, our total area, A, will be pi over 12 plus pi over 32. And we can go ahead and simplify that to be 11 pi over 96. And that's our final answer.